Should I start? Okay. All right. Well, first, let me thank Christina and the other organizers for this opportunity. And so the title I picked is slightly different from what you could see because I want something generic, because I'm going to talk about two things, but one very quickly related to what we saw this morning, and then turn to more astrophysics to have a change of scenery for a bit. So I'm an N3S fellow at NC State University and UC Berkeley, and the main work I'm going to talk about was done with these collaborators, mostly at NC State. So first, Sergio mentioned some recent work that I'm going to advertise quickly, which builds on these 2-3 decades of tremendous work and progress in the community of neutrino evolution in the early universe with Sergio, Stefano, Cristina, and Netta, and many other people that I can't mention everyone, it would take 2 hours, where mostly the goal of this community was to solve this equation more and more precisely in different scenarios and so on. This is the quantum kinetic equation that you heard about. And in this paper, the example is the evolution of asymmetries. That is, you assume a difference between neutrino and anti-neutrino distributions at high temperatures, 20 megaelectron volts. So we don't assume some low reheating or something. It's, let's say, standard reheating. And as you can see, the 3 colors are for the 3 flavors. These asymmetries evolve dynamically. You have the effect of collective oscillations and down to some freeze out at lower temperatures. The one thing that is possible now, thanks to all the progress in the community in the last decades, is to include those very interesting ingredients: 3 flavor mixing, a full collision term, no damping approximation, because at least for the evolution of asymmetries, it's quite important to have the true collision term. QED corrections to the plasma thermodynamics, some adiabatic-like approximation to deal with the separation of scales in a problem. And with all that, we can connect primordial asymmetries at 20 and larger MeV down to the BBN epoch. And the one thing we know, sort of, is that you need a very small asymmetry in the electron flavor at the BBN epoch, because otherwise you create too little or too much deuterium, helium, and so on. But a big question is, how do you connect these initial values that come from any model that you want to design to the BBN epoch observables? And just to give one example of results, using constraining N effective with CMB data and the primordial abundances of helium and deuterium from existing measurements, this is a plane of the electron flavor asymmetry, and on the x-axis, the average asymmetry of all 3 flavors, assuming identical muon and tau asymmetries. And this is the likelihood ratio, and you can see that all these bright yellow regions are really high likelihood regions. So essentially, it's very hard to constrain those primordial asymmetries for now, because as you could see here, initial asymmetries sort of equilibrate to an average value. So you sort of really reduce those asymmetries. And what we showed is that in the future, with future CMB experiments, which will much tightly constrain N effective in particular, it should be possible to close these contours and start being able to really put significant constraints on models predicting some residual lepton asymmetries. So one thing I want you to remember from this part is that in the early universe, we can do what was mentioned to be precision cosmology. Because, I mean, at least to me, it's mostly because it's homogeneous and isotropic. Fantastically simple in terms of at least that. That's what allows to reduce the dimensions on integrals and so on. And since it's a dense environment, we have very interesting physics, evolution of asymmetries, stellar neutrinos. You can do many, many things. Another example of dense environment is astrophysical environments, core collapse supernovae, neutron star mergers, in which it's not homogeneous and it is not isotropic either. And this is both a curse because we cannot do as precise things in a way, but it's also a blessing because many, many new phenomena can appear and in terms of flavor conversion, and that's what I'm going to talk about now. One big question in this astrophysical community is, how do neutrinos change flavor in those environments? We want to know that for nucleosynthesis purposes, to know the signals from those objects and so on. And I'm going to talk about a much tighter question here. It's the notion of neutrino flavor instabilities in binary neutron star mergers. It's based on, I just mentioned those 3 papers that we published in the last 2 years. So in this talk, I'm going to focus on, you're going to see this slice a lot. It's a slice from a neutron star merger simulation done by François Faucard and collaborator at the University of New Hampshire. It's a general relativistic radiation hydrodynamics with collision for neutrinos using the NewLib library for people who know. And this is a snapshot taken 3 milliseconds post-merger. This color map shows the matter density. So you see the very dense core and the tidal arms with this spiral shape. And this is what is called an M1 simulation, which means that because it's anisotropic and inhomogeneous, you cannot just, it's very hard to solve for the evolution of neutrinos in all angles, at all places, at all times. So this simulation uses what are called the angular moments. That is, instead of looking at all the angular directions, you integrate over all angles at a given point that gives you the number density. You do the same to look at the overall flux in one given direction. And you write your system of equation just as a function of these 2 quantities, and that is called an M1 scheme. I will show later why we need what is called a closure to close the system of equation, because you start from a sort of infinite number of equations for all angles down to just equations for these quantities. So there is an additional assumption that closes the system of equations. And it's equivalent, you can remember, to assuming that the angular distribution of neutrinos at each point has a given functional shape. The one thing of these simulations, so there are many different groups with different simulations, no flavor mixing. Neutrinos are treated classically in the sense that you have an electron flavor neutrino, electron antineutrino, and the rest of neutrinos. It's called nu E, nu E bar, and nu X. And they have no mixing, which we know is like not true in actual life. They would mix and there would be some additional flavor change. And we want to know how the flavor would change in those environments. Since it's very dense, you have a very high density of neutrinos, of matter components. There are many, many flavor conversion mechanisms, and I refer you to the recent review by Christina, which covers mostly everything that is known about these different mechanisms. And I will focus in this talk on 2 recent, or less recently discovered mechanisms. First, what is called the fast flavor instability. Fast because it is just fast in terms of time that it takes. It happens on timescales of a nanosecond, where those large simulations, they have time steps that don't go below a microsecond, like clearly not. So nanosecond is a very, very subgrid component of what really happens in the system. And these instabilities are related to what is called an angular crossing between neutrino and antineutrino distributions. You take a given point in your neutron star merger and you look at the neutrinos coming from the left, neutrinos coming from the right, antineutrinos coming from the left and the right. If you have more, that's what this sketch shows. If you have more neutrinos coming from the left than antineutrinos, and on the right you have more antineutrinos than neutrinos, if you look at the number of neutrinos in each direction, there is a crossing in one region, more neutrinos, one more antineutrinos. And it has been shown that this will lead to an instability. By instability, I mean that you take just neutrinos in pure flavor states, you slightly perturb that, and you will have some, here very fast, flavor conversion because this flavor field is not stable. And I will show you how we can describe that precisely. An additional instability is called the collisional flavor instability, found by Luke Jones in 2021. When you have different collision rates between neutrinos and antineutrinos, it can also trigger an instability that happens, though, on much larger timescales. To describe the system, we use quantum kinetic equations, which we've heard about several times today. It's a way to combine kinetic theory, the Boltzmann equation, including flavor mixing. And the object that we evolve is a generalization of the usual distribution functions, which tells you how many neutrinos you have at a given position for a given momentum. In what follows, I'm going to use the 2 flavor approximation, only electron flavor and X flavor. See that as a muon or tau neutrino, whatever you prefer. And so we cannot just use the distribution functions because of flavor mixing. We need this 2x2 here density matrix, where the off-diagonal components describe this, what we call flavor coherence. and the diagonal elements are a sort of generalization of those usual distribution functions. The evolution equation in those neutron star mergers I'm interested in is a certain version of a quantum kinetic equation. You have on the left a time derivative and the advection term, advection that is not present in the early universe, but here you clearly have to take it into account. Collision term, and there is a Hamiltonian with all those mean field contributions. And for the fast flavor instability, it's driven by the self-interaction, that is the mean field potential due to neutrino interactions with other neutrinos and antineutrinos. This term largely dominates, so it's the only one I'm going to consider. As you can see, it's proportional to the difference in the densities of neutrinos and antineutrinos. So if we want to know where the flavor field is unstable, linear stability analysis is a great tool, very efficient, and what would be the word? Adaptable. So since I said this fast flavor instability is related to the existence of an angular crossing, we need a priori to follow all the angles. Even though we used a moment simulation, we need to reconstruct the angular distribution and perform the analysis. The way we do it mathematically is to write the density matrix in a given direction. The diagonal elements are taken from the simulation. It's the classical quantities. And we perturb the off-diagonal with a plane wave. If the frequency has a positive imaginary part, this will correspond to a time growing exponential. That's an instability. So your flavor field initially is flavor diagonal, and on a given time scale, the off-diagonal terms will grow exponentially. That is literally an instability. As I said, diagonal elements are taken from the NSM simulation. Now you could ask, I said we were using moments, how can I get the angular distribution? So let me quickly explain that. The classical simulation we're using uses what is called the maximum entropy closure, which corresponds, for my purpose here, to assume that for a given flavor A, the angular distribution of neutrinos has this form. It's a exponential cosine theta, where these different parameters, n is the number density, and z is given by this equation. This is the flux factor, and that gives you a sort of egg-like shape of the distribution. To show you one example of one point in the simulation, here you have this is called the maximum entropy closure distribution of, in red, antineutrinos and in blue, neutrinos. You have here as a function of this polar angle. And you can see indeed the existence of a crossing here, the red and blue curves cross. So this is an unstable point. So we can do that on every point of the simulation. Write the QKE, write it as a function of this perturbation that gives you a pretty big matrix depending on your angular resolution. You look for eigenvalues that you scan for all possible wave vectors. And overall, you will have a given mode with a given k corresponding to the largest imaginary part of omega, that is the fastest growing mode, corresponding to what I will call the instability growth rate. The one thing I want to highlight is that we need, for that to diagonalize, we have to do that for neutrinos and antineutrinos, hence the factor 2, times the number of angular bins. So let's say you take 100 angular bins, which is typical. That's 200 times 200 matrix, which you can diagonalize pretty quickly for one matrix. But when you do that on every point of the simulation, that is very, very time consuming. Here are the results on the same slice I showed you at the beginning. So you have the color scheme shows you the instability growth rate in this equatorial slice. On the left, we don't include collisions. So that's what people have been calling a pure fast flavor instability. And if you get additional instability on the right, we can sort of safely call it a collisionally induced instability. The first thing I want to mention is the values. For the fast instability, the growth rate is typically 10 to the 10 per second. So it's below the nanosecond. You will have these changes to the distribution. This is a tremendous challenge for the simulations, because if you have a large scale simulation and something happens at the nanosecond level and you can only take, I don't know, a microsecond step, you need a good subgrid model to take that into account. In addition, you see that there are regions where collisions actually induce some flavor instability. It has been questioned whether it was relevant or not. Well, there are some like it's several kilometer scale regions where this happens. However, when we look at the growth rate, it's given typically by the collision rates. So this is a scale that actually should be described concurrently with the large scale evolution. So what this shows here is that it's not necessarily a subgrid model that you need, but you sort of need to do all that at the same time, which is going to be very hard. I've talked about a moment simulation, and one goal that we had was to try to develop such a linear stability analysis just using moments without having to reconstruct this angular distribution, trying to do that directly at the level of moments, which would be much faster and in a way more self-consistent. I realize I haven't put it before. The definition of these moments I've been talking about a lot. You have your density matrix and you can integrate it over the angle of P. If you just do an integral over all the solid angles, that's a number density. You do it in a given direction, that's the flux. At rank 2, that's the pressure tensor, and so on and so on. You do that operation to the quantum kinetic equation, and you get those first two equations, which are the moment QKEs. As you can see, the second equation, that's the equation for the flux, it involves the pressure tensor. And if I wrote the equation for the pressure tensor, you would get the order 3 moment, and so on and so on. So that's why I said that we need a closure, because if we just want an evolution equation for n and f, we need to get rid of that p. But we cannot just say p is 0. That would be completely wrong. We need to express p as a function of n and f in a physically justified way. And that's the maximum entropy closure is one of these choices that has been very studied in literature. There are some regions where we know it's not very good description, but this is what was used in the simulation we used to get our data from. So that's our starting point. So if we just use moments, we can do the same linear stability analysis. The diagonal elements are this time directly what we have from the simulation. We perturb the off-diagonal and look for a positive imaginary part of omega. The maximum closure that is used in the simulation, the classical closure, is, I sort of need to explain a bit more what it is. It's a proportionality, if you want, between the pressure tensor and the number density. The proportionality coefficient being given by this functional form, polynomial form, and it's a function of the flux factor. What that means is if your flux is 0, which means that it's isotropic at 1/3, we know that the pressure has to be 1/3 of the number density if it's isotropic. If instead you have the flux factor that is 1, which means that all your neutrinos are traveling in the same direction, this chi is equal to 1, and indeed the pressure tensor in that case, all the moments are equal to n in the same direction. So, and then you have a sort of interpolation between those two limits. This is the classical thing, but we have a flavor matrix now, so we need to do something for the flavor of diagonal elements. And there is no, I mean, a priori, we don't really know what to do. There is no recipe that has been established before. So what we've been using is I call that quantum extended. I'm going to say semi-classical. We use the same proportionality coefficient, but calculated with a sort of average of the fluxes of the E and X flavors. It's we take a flavor trace, essentially. It's a way to say that this off-diagonal element has a behavior that is sort of described by the mixed effect of the E and X flavors. But this does not have to be true. And I'm going to show that it works, but not perfectly. We apply this to the QKEs. We get a matrix equation once again. We diagonalize the matrix, but this time it's an 8x8 matrix. Remember the 200 times 200 matrix. This is so much faster. These were the results with the multi-angle analysis that I already showed you. This is sort of, if you want, the truth. And these are the results using moments. I don't know, I guess you think it looks similar. That's what people usually tell me. But to me, it looks different because you look at them all day long. But mostly what we can highlight is that the main regions of instability are really well recovered. like the bulk of the instability, it's found with growth rates which are very comparable. However, we have all these new instability regions which are not existing here. And all these differences are limitations of the closure. We do not expect the closure for the off-diagonal elements to describe perfectly the physics of the system, and that is the consequence. However, when you compare left and right, so the additional effect of collisions, you find some new regions, notably remember this arm of instability in the center. Same behavior here. We have the same new regions of instability, which is a good sign that our moment method is able to describe the additional effect of collisions. Now, I said that limitation was the closure. Let me highlight this. On the left, it's the multi-angle result. On the right, it's the moment result without collisions. So I will not discard collisions until the end for now. So here you can really better see, I would say, the similarities and differences between the two methods. For this, the closure that we use for the off-diagonal element is this flavor trace sort of mixed flux proportionality coefficient between E and X. One thing we can do is to, since we have these results, I can look at the fastest growing mode and look at the, since it's multi-angle, I have the full distribution of eigenvectors. I can compute the pressure, the number density, the flux for these, and reconstruct what should be the true relation between P, EX, and NEX. That's what I do here. And as you can see, the agreement gets much, much, much better. It is not perfect because what I do is I generally input for this closure relation the true closure relation, but only for the fastest growing mode. Remember, I scan for all values of K, and I pick the value of K with the fastest growing mode. I find what is the true relation, and I put it here. So if this relation is not necessarily true for other wave vectors, so maybe what happens is that, I don't know, here, I have another K which gets a faster, spurious, if you want, faster growing mode, and this is what I eventually get. So this method is clearly not perfect, and in addition, it requires to do the left first, so no improvement. But this shows that moments, sort of, if we know the truth, we could find it very accurately. So we are now working on designing and understanding better how the closure should be designed so that we can get in the various regions of interest the best possible results in the shortest possible time. All right, so yeah, I wanted to free you at 3:30, so that's great. The main message of this main part of the talk is that moments can describe those fast favor instabilities. Even though they are truly anisotropic features, we can describe them with moments, which is, I think, great. Linear stability analysis, which is what I've used here, is technically cheap. You just have to diagonalize the matrix. It's not a full dynamical calculation. So it's great to explore where and how the flavor field will be unstable. And we can sort of use it to know how different closures will perform compared to the truth. The shortcomings of the method are indeed this, as long as we won't know what is, if you want the perfect closure, it will still be imperfect, but we can get better and better. And I also highlight collisional induced instabilities seem to be present in neutron star mergers, and that shows that they should be taken care of, or at least included in the future works. Overall, this work that I showed is a step towards this goal of the astrophysical community here on including flavor transformation in large-scale simulations, because this is the major milestone that remains to be done to have a full confidence in nucleosynthesis yields, signals from supernovae, whether or not a supernova explodes, and so on. So on this conclusion, thank you.
So thank you. Actually, you were not on time, but ahead of time. So there is time for some question or comment.
Okay, so I have 2 comments. First of all, as you know very well, there have been lots of studies of flavor conversion in neutron star mergers. Yeah. So with respect to what you said at the beginning, so we know that there are also fast flavor conversions. So there is a vast literature about the implementation of
The collisional is more discussed.
No, but these collisional instabilities, as you know, are much more recent.
Yeah, but the fast flavor is well established.
Fast flavor very established and has been studied in many places. And collisional instabilities have been studied a lot in supernovae. So there is a huge literature. And also these moments, quantum kinetic equation are regularly used in supernova simulations for the transport. So all these methods are known, except for the closure in presence. Okay, this particular aspect is new. And I also wanted to add concerning the review that I wrote, that this review is not only, as you know, on all many new flavor conversion phenomena that have been discovered in the last 15 and more years. In fact, it's even more than that. But it also concerns all the approaches, theoretical approaches that have been developed and currently used in the field. So mean field, extended mean field, quantum kinetic equations, linearized equations, and the many body and all the connections to the new other domains like quantum information theory, entanglement, and it has a last part on observations, in particular for supernovae and the diffuse supernova neutrino background. So
I highly recommend the reading of these reviews.
Okay.
Comments, question? Actually, I have a question. So you have shown the use of 2 moments, right? Have you tried to see if you use another moment and cross-check how well you do with the 2 moments?
So for this, let's call it quantum study, no, because we don't have the 3rd moment available. But it's been, so I'm not an expert in that, but the one thing I know is that two moment scheme are shown to be, there is some stability criterion that is satisfied. And if you include a 3rd moment, you can get some mathematical instability. And it's actually not necessarily better. Okay. However, one other thing that was shown is that if you do a full multi-angle calculation and you look at the power in each moment, unfortunately, it does not go to 0 as you increase it. Like there is power going to smaller and smaller scales. So that's why ideally, if you have a perfect closure, you describe that perfectly. But any imperfection of the closure will at some point be a problem. So yeah, moments are an imperfect solution to a very complicated problem, but this is, for people know about that and have been studying that a lot, so.
Just a curiosity. I am more familiar with the supernova. So the fast conversion actually happens in a very, there's a distance inside the neutrino sphere. So it's a peculiar characteristic. So here the distance is important. The point in which this happens are important or not?
Yes, so if you, so it's harder to define a neutrino sphere here, but like sort of if you want the equivalent of a neutrino sphere in terms of flux factor would sort of be basically that shape, that inner circle is one of these. So it seems also in neutron star mergers to be sort of localized in that, but we actually have, if you take, for instance, a transverse slice, you have many more regions. It seems to be less localized than in supernovae, at least from what I know. So I might be a bit incorrect here, but I think that's the feeling in the community, that it's more ubiquitous in neutron star mergers than in supernovae, where it would be more localized.
And this is the problem, since in supernova, since they are very localized, it's a sort of step by step, okay? Instead here, I have the impression that everything overlaps, so you could have a fast transition simultaneously with the normal or slow oscillation. So how could it be possible to mimic this mess? This is my point.
The one thing that could save us is the fact that these are so fast. So,
okay.
Yeah, so some people are designing, and it's criticized by others, but to basically, I don't know, you have a machine learning model that predicts for a given classical flavor field what will be the outcome of flavor transformation. Well, every time it's unstable, You apply that, you get your final state, and that's your new input. That would be a subgrid way. There has been other proposition like a BGK model to, you also need to know the final state, but where this time scale would be the sort of damping scale going to that new state, and you could sort of include that. I am sort of much more confident that we can do something with the fast instability than the collisional, because at least you have a separation of scales. So you can probably, yeah. For the collisional instability, it seems like if you want to know how collisions affect your classical neutrinos, you need to know how they affect your quantum neutrinos too. So that would be a huge challenge.
Actually, I'm curious about the scale. So these scales are larger than the size of the system, right?
What do you mean?
This is you're talking about neutron stars, right?
Yeah.
So this is larger than a neutron star.
Oh yeah. So that's after the merger, like the hypermassive neutron star is honestly this white circle. But yeah, so we look at the entire disk around, and yeah, that's also where you want to know the instabilities, because that's where neutrinos travel toward, and where nucleosynthesis can happen and so on.
Comments or questions? Otherwise, I think we go for coffee before we Julian. Thank you.